So after you have learned Rutherford's alpha scattering experiment, the next one will be the model of an atom. Although Rutherford's experiment by itself doesn't give you the model of an atom. So it was the work of scientists after that which gives you the model of an atom. So when you look at the model of an atom, you will notice that if they ask you to describe, so we know the nucleus is positively charged, which contains protons and neutrons, and you have electrons which are negatively charged orbiting it. And the idea is the number of protons in the nucleus must be equal to the number of electrons orbiting it, because the atom is neutral. Okay, so that's what you learn in chemistry as well. Now, another thing I just want to add is that the diameter or the size of an atom and the diameter or the size of a nucleus. So if they ask you for the diameter or size of an atom, is about 10 to the power negative 10 meters, whereas the diameter or size of a nucleus is about 10 to the power negative 14 to 10 to the power negative 16 to 10 to the power negative 14 meters. Okay, so you need to know this range. Now, how do we compare them? You can imagine, right? They always use this comparison. If you watch American football, then you will notice the size of the field is huge, right? Now, if you put the football in the middle of the field, that is like your nucleus, and the whole field is like your atom. So that's how small your nucleus is compared to your atom. All right. So the next one we're going to learn is what is a nucleon number and what is proton number. Now, whenever you write the symbol for a nucleus or an atom, we can write in this form. Now, this kind of symbol, you can use it to represent the nucleus or represent the atom. If you are using it to represent the nucleus, then we don't have to talk about electrons. But if you're talking about an atom, then you have to talk about the electrons. For example, if you look at this, 16, 8 oxygen, so proton number is 8, means it has 8 protons, right? Then 16 is a nucleon number, which is the total number of protons and neutrons. So if you subtract 8, which is the number of protons, you get number of neutrons, which is 8. So from here, we will know there are 8 protons and 8 neutrons. So like for this one, aurum, which is gold, so 79 proton number, that means it's 79 protons. 197, which is the nucleon number, so when you minus, so you get 118 neutrons if you take this minus this. Okay, now if they ask you for an atom, then you will add in another 79 electrons. But if it's nucleus, then you don't have to talk about the electrons. But I just want to also highlight something. Do you know the symbol for an electron is actually this? 0, negative 1 e, right? So in this case here, the proton number is -1. So does it mean that it is a number of protons? No, right? So generally, generally, proton number actually represents charge. But for a nucleus or for an atom, then the proton number also represents number of protons. But not necessarily true for all cases. That means, like for example, electron, the proton number does not represent number of protons, just the charge. So generally, if you say charge, yes, correct for all cases. But if you say proton number represents number of protons, it is only for a nucleus or helium, nucleus or an atom. Do you understand that? Okay, that's the idea here. So the next one you're going to learn about is an isotope. What are isotopes? Now, in your syllabus, maybe in chemistry you have learned that isotopes are atoms with the same number of protons but different number of nucleons. But for our physics, we won't use atoms, but we will use nuclei, which is the plural for nucleus. So we will say the isotopes are nuclei with the same proton number but with different nucleon number, which means to say they will have the same number of protons but different number of neutrons. Like for example, your neon here, all of them will have 10 protons, but since they are all different isotopes, then they have different number of neutrons. It will be 10 neutrons, 11 neutrons, and 12 neutrons. Now, you don't have to learn about the properties of the isotopes, like do they have the same chemical properties or physical properties. That one is not in your syllabus, okay? So you just have to know this only, okay? Because I think in chemistry, they also talk about the properties. Now, during nuclear processes, which we're going to talk about in a short while, which is fission, fusion, and decay, we will be learning how to write the nuclear equations to represent the process. Now, in each of the nuclear reaction, you will need to know what are the quantities which are conserved. So let's go through them one by one. Firstly, proton number must be conserved. Now, remember the bottom part here is a proton number. So if you notice that before the reaction, if you add up the two proton number, you get 9. After that also you add up, you must get 9. Then for the bottom, you add up, you get 6. And then this one also you add up, you get 6. So that's called conservation of proton number, right? Now second one, conservation of nucleon number, which is on top. So if I add the two numbers on top, I get 18. This one I add up 2, also I get 18. This one I add up the 2, I get 13. This also get 13. So this must be true. Now third one is mass energy. Now mass energy is actually a new concept. Remember in your topic of work energy power where we said that energy is conserved? We call it the principle of conservation of energy. Now later on when Einstein came up with some theories, he said that this conservation of energy is wrong because energy is not conserved. In fact, what is conserved is mass dash energy. That means instead of saying that the total energy of this universe is conserved, the correct way to say it should be the total mass and energy in this universe must be conserved. Now why? Because according to Einstein, your mass can be converted into energy. Energy can also be converted into mass. They're always changing. So therefore you need to total up both of them together. Then only you'll be conserved. So then people ask me, then why do you learn the wrong thing? Conservation of energy, right? Now, conservation of energy would be for most cases where we can see it. For example, let's say you're talking about a car or a person moving from one point to another, then conservation of energy is a very good approximation of what really happens. But if you go into like very, very small particles like the nucleus, all right, we talk about protons, neutrons, the mass of these protons and neutrons and the electrons. Then we go really, really, very small. Then you will notice there's a tiny, tiny change in mass, which actually is due to change in energy as well. But in in usual life, do you actually look at protons and neutrons or electrons? Can you see them? You can't really, right now. So therefore, for us, it seems that conservation of energy is true. Unless you go much, much smaller, then only you realize it's wrong. Okay, so we still talk about conservation energy for most cases. Only when you go into nuclear physics, then only we talk about conservation of mass dash energy, because that is the real actual case. Okay. Now, so fourth one, linear momentum is conserved. So you can also use conservation of momentum to represent nuclear processes. If you remember in the topic of dynamics, we talk about explosion, which is nuclear decay. Your conservation of momentum still applies. All right. Now, there are a few things I want to talk to you about now. Now, some people say when the proton number is conserved, does it mean that number of protons is conserved? The answer is no. How come? Now, I remember I was telling you proton number actually represents number of protons for a nucleus. But for an electron, does the proton number represent number of protons? No. So therefore, you cannot say number of protons is conserved, especially when it involves, when a nuclear process involves electrons. For example, beta decay. Because in beta decay, a neutron actually splits to become a proton and an electron. There's a beta minus decay lah. In the beta plus decay, then a proton splits to become a neutron and a positron. Okay, which we will learn that later. So then your number of protons is not conserved. Okay, so charge, yes, because charge is your proton number, but number of protons not always conserved. Okay. Right, next one, what about nucleon number? Yes, because nucleon number represents the total number of protons and neutrons for nucleus one, so that one is conserved. Alright, but is number of neutrons conserved? No. Because using the same example of beta minus and beta plus decay, which is electron or positron decay, your number of protons and number of neutrons actually change. Okay, like for example in beta minus decay, one neutron will split to become a proton and an electron. So you have excess one proton, all right, and your neutron will lose by one. Similarly, in beta plus decay, which is positron, your proton will become a neutron and a proton. Positron, sorry, a positron. So therefore, your number of protons will decrease by 1, your number of neutrons will increase by 1. So number of protons and number of neutrons are not fixed. They are not conserved. But you say proton number and nucleon number, they are conserved. Okay? Now, in every nuclear reaction, and the 3 of them which we will learn will be fission, which is splitting of a heavy nucleus, fusion, joining of lighter nucleus, or decay, which is random and spontaneous. Also a splitting, that's called decay. We can actually write equations to represent them. And there are 4 things which are conserved. So let's go through them. You're going to memorize this. First one is proton number is conserved. So if, for example, you look at this nuclear reaction, alright, can you see that initially your total proton number is 7 plus 2, which is 9. After that is 8 plus 1 is also 9. So that's what you mean by conserved. The second one, 4 plus 2, 6. 6 plus 0, 6. So you always must be conserved. The second one, nucleon number, which is the number at the top here. So it must always be conserved. So for example, this 14 plus 4, 18. 17 plus 1, 18. 9 plus 4, 13. 12 plus 1, 13. Right? And the third one, which is conservation of mass and energy. Now this is something new. Because when you were in the chapter of work, energy, power, we learned this principle of conservation of energy. Now when Einstein came, he said that this principle is wrong. Because energy is not conserved. He says that mass and energy together are conserved. That's why we call it conservation of mass and energy. That means if you were to find the total energy in this universe, it is not constant. But if you find the total mass and energy in this universe, that is constant. Because mass is changing to energy, energy is also changing to mass. Alright, but then how come in the chapter of work, energy, power, we said principle of conservation of energy? So aren't we learning something wrong? So actually, conservation of energy is more like for bigger objects. Then you won't be able to see the change in mass. For example, let's say you are running, let's say Q is running up the slope. Alright, when he runs up, the sea suddenly becomes smaller. Let's say it runs up higher and higher, then it shrinks and then becomes nothing. It doesn't, right? That means mass becomes energy. No, it doesn't work like that. For bigger objects, conservation of energy seems to be a good approximation of what happens. But when you go into very, very small particles, like nucleus, in the nucleus you have protons and neutrons. If you were to weigh them, the protons and the neutrons, before and after they form a nucleus, before and after they form the reaction, you will notice a very tiny change in mass, which becomes significant because the mass of the nucleus or the mass of the protons and neutrons themselves are small. So a small change in mass is a big percentage change. But for us, right, we will never realize it because our mass is so huge, so our change in mass is almost nothing, so we don't feel it. So it's not to say it's wrong, but it's just that for when you go down to nuclear level, then the change in mass is noticeable. So therefore, when we talk about conservation of mass energy. Okay, now what about the last one? Linear momentum is conserved. So principle of conservation of momentum still applies. For example, when we were doing dynamics conservation momentum, we use the explosion. Remember the conservation momentum for explosion. So nuclear decay also fulfills the principle of conservation momentum. Means the initial momentum 0. So after the decay, both particles must move in opposite directions. So it still applies. This form. Now, on another level, okay, they will also ask you more about this conservation of proton number and nucleon number. Right, to be careful about it. Now, some people said if proton number is conserved, does it mean number of protons is conserved in a nuclear reaction? So the answer is no. You know why? Proton number represents number of protons if you are talking about a nucleus or an atom, right now. For example, let's say you say the proton number of alpha is 2, that means there are 2 protons. But if you were to consider, let's say, an electron where the symbol is 0, negative 1 e, does the negative 1 here represent number of protons? Yes or no? Does an electron have a proton? No. So the negative one here represents charge, not number of protons. So if you were to include beta, which is beta minus and beta plus is a positron, which is 0, positive 1. They put there beta plus, so this symbol, beta plus, okay, beta plus. So what will happen is your number of protons won't be conserved. You know why? Example, how you get a beta minus decay, which is this beta minus decay, this one, how to get a beta minus decay is when a neutron splits to become a proton and an electron. In a beta plus decay, a proton will split to become a neutron and a positron. You understand? So what will happen here is, before the reaction and after the reaction, you will access one proton. So number of protons not conserved. In the case of beta plus decay, before and after you have less one proton because one proton decayed already. So number of protons not conserved. But if you say charge, then it's conserved. Because you see, I want you to understand, proton number represents charge in all cases. Whether it is a nucleus or electron, proton number represents the charge. Do you understand? That's why this negative one here and positive one here represents the charge. But in cases of nucleus and atoms, then it also not only represents the charge, but also represents the number of protons. Do you understand? So you want to say number of protons is conserved is wrong, because you are not including electrons and positrons yet. Understand? But you say charge is conserved is correct. Understand? So number of protons not conserved, but charge is conserved. Alright, proton number conserved, no problem because proton number is the same as charge. What about nucleon number? We said nucleon number is conserved, yes, but does it mean your number of neutrons is conserved or not? Now, since your proton number is conserved, your nucleon number is conserved, does it mean that your number of neutrons is conserved? The answer is no. Because if your number of protons is not conserved, then the number of neutrons cannot conserve, because you add up together to give you a nucleon number. Do you understand? So just be careful about it.